Unlock the potential of artificial intelligence. Welcome to Deep Learning and Generative AI.
This is part 3. So we've already covered the foundations, everything from RegNet all the way up to ResNet. Now we're jumping into the modern era. We're going to explore how designing these networks really evolved from this handcrafted art into a systematic science, and then finally into a powerful tool that pretty much anyone can use. So yeah, let's dive in.
Okay, so our journey from 2017 to today really follows 3 big pivotal shifts. First up, we've got a radical refinement in how networks handle information, and that's DenseNet. Second, a complete paradigm shift, moving away from all that manual tuning to a systemic scientific discovery with RegNet. And finally, the breakthrough that brought all this power to the masses, the application of transfer learning. Let's break each one of these down.
All right, first up, DenseNet. So the big question that designers were grappling with as networks just got deeper and deeper was this. How do we stop vital, low-level information from getting lost or just washed out hundreds of layers down the line? How do you make sure the signal from layer 1 can still be heard loud and clear by layer 100?
And this slide, this perfectly contrasts ResNet's solution with DenseNet's. ResNet, if you remember, used summation. It added the input of a block to its output. It was kind of like a clean game of telephone. But DenseNet does something way more extreme. It doesn't add, it concatenates. It builds this collective knowledge by giving every single layer a direct connection to the feature maps of all the layers that came before it.
Yeah, this idea of concatenation is the real secret sauce here. Instead of merging information, you're literally just stacking it. You're preserving everything. And mathematically, this is just fascinating. While you can think of ResNet as a kind of Taylor approximation, DenseNet is more like creating a higher-order series. By concatenating these increasingly complex functions, it can model incredibly rich interactions between features that were learned at totally different stages.
But of course, if you just keep stacking features, you're going to run into a very practical problem, a channel explosion, right? The depth of your feature maps would just grow uncontrollably. So to manage this, DenseNets very cleverly insert what they call transition layers between these dense blocks. And these layers use super efficient one-by-one convolutions to compress the number of channels back down, acting like a control valve on this information superhighway.
So this table really highlights the key trade-off. DenseNet offers these incredible advantages. Fantastic gradient flow, because every layer is basically connected right to the loss function, and just shocking parameter efficiency. But there's a catch, and it's a big one, the computational cost. All that concatenation requires copying tensors around in memory, which makes DenseNets way more memory hungry than ResNets.
And that brings us to our second major shift. You see, the field was kind of getting bogged down. Designing architectures like ResNet and DenseNet, it was becoming an art form. It relied on a lot of intuition and trial and error. The next revolution was about moving away from this sort of artisanal approach and toward a truly scientific, statistical way of discovering the principles of good network design.
This slide just perfectly illustrates that shift in thinking. The old way, manually tuning dozens of hyperparameters, depth, width, group convolutions. It was biased and just totally unsustainable. The new paradigm, what's called design space exploration, doesn't try to hunt for one perfect set of parameters, no. Instead, it designs a whole distribution of models to find the statistical principles that define a good design space.
And to do this, researchers created this generalized template called the AnyNet design space. As you can see, it has a pretty standard structure, a stem for that initial processing, a body with multiple stages, and a head for classification. But, and this is the key part, parameters like the depth and width of each stage were left free to vary, creating this huge space of possible architectures.
And the size of this space is astronomical. We're talking more than 10 to the 18th possible network configurations. You could never, ever search through all of those with a brute force approach. It's completely impossible.
So they came up with this brilliant metric. Instead of looking for the single best model, the proverbial needle in a haystack, they decided to look for the best haystack. They sampled thousands of models from a design space, trained them just for a little bit, and then plotted their error distribution. A better design space, like curve B here for RegNet, is simply one that has a higher density of good models. You're just much more likely to find a winner in there.
And out of all this statistical searching came these beautifully simple, elegant design principles. Things like the optimal network width should increase linearly, the stages should get deeper as they process lower resolution feature maps, and surprisingly, those complex bottlenecks that were used in other models, turns out they were often not necessary.
And these rules led directly to the RegNet models, which were simpler, faster, and more accurate than their manually tuned competitors. This brings us to the final and maybe the most practical innovation of all. Okay, so we have these incredible, scientifically designed architectures, but they're trained on massive datasets like AnyNet. What if you're, say, a hospital and you only have 1,000 medical scans? How can you tap into all this power?
Well, the answer is transfer learning. And the core idea is really simple. Don't start from scratch. Take a model that has already learned to see the world from millions of general images on AnyNet and then adapt that powerful pre-existing knowledge to your own specific, much smaller dataset. This saves an enormous amount of computational cost and, crucially, it helps prevent overfitting.
And the reason this works so well is explained by what's called the feature reuse hypothesis. See, deep networks learn a hierarchy of features. The earliest layers learn universal concepts, kind of like the physics of images. You know, edges, curves, textures. The middle layers learn more complex patterns. These features are highly transferable. It's really only the final layers, the semantic layers and the classification head, that are super specific to the original task.
So, the practical process, which is called fine-tuning, is pretty straightforward. First, you initialize your network with the weights from the pre-trained model. Second, you swap out the final classification layer, the head, for a new randomly initialized one that matches your new set of classes. And third, you just train the network on your new data, optimizing the weights starting from that really powerful initial point. Now, there are two main strategies for this. Strategy A is the most conservative. You freeze the entire pre-trained body and only train the new head. You're basically treating the network as a fixed feature extractor. Strategy B is to fine-tune all the layers, but you do it carefully. This is done with differential learning rates. You use a really small learning rate for those deep, stable layers and a larger one for the new, task-specific layers near the end.
Okay, so let's put all of this together into a practical playbook. Given a new task, how do you decide which of these transfer learning strategies is the right one for you?
This transfer learning matrix is an incredibly useful guide. It all really depends on two factors: the size of your target dataset and how similar it is to the original source data, like AnyNet. If your data is small but similar, you'll want to just freeze the body and train the classifier to avoid overfitting. If it's large and similar, great, you've got enough data to fine-tune all the layers. If it's large and different, well, the source features might be irrelevant, so you might need to train from scratch. The tricky zone is small, different data. There, you risk overfitting, so maybe a partial freeze is your best bet.
And this slide really summarizes the entire arc that we've just discussed. We started with the architectural refinement of DenseNet, which maximized information flow. Then came the systemization with RegNet, which discovered design principles statistically. And finally, we arrived at widespread utility through transfer learning, which democratized access to all these powerful models. What this all signals is a fundamental shift in how AI is actually built. The long, hard work of manually engineering features, that's over. And as RegNet showed us, the era of manually engineering the architectures themselves is also ending. We are now firmly in the era of foundation models. And that leaves us with a final, provocative question to think about. As the design of the models themselves becomes more automated and standardized, what becomes the key human skill? Is it defining the problem correctly? Is it curating unique datasets? Or maybe it's understanding the limitations of these incredibly powerful systems? Well, that's the challenge for the next generation of AI practitioners.